Greetings and salutations, magical chemists. Let's talk about titrations, stoichiometry in action. In a titration, a substance of known concentration, the titrant, which is found in the burette, is reacted with another substance of unknown concentration, the analyte. In general, we titrate until we reach the equivalence point. Now, the equivalence point is the point in time at which the moles of each reactant are stoichiometrically equal to each other. For an acid-base titration, this means that the moles of your protons are going to be equal to the moles of hydroxide, and thus the acid and base are both completely neutralized. However, you're kind of hard to tell sometimes if you're at the equivalence point, because usually an acid and a base look exactly the same, like water. So we often titrate to the end point. We use an indicator which changes color, and the point in time at which it changes color, that's officially known as the end point. Our goal is to choose an indicator where the end point is the equivalence point. It's actually pretty straightforward to choose an indicator that will change color at the equivalence point of your desired titration. All you're going to do is choose an indicator where the pKa of the indicator equals the pH at the equivalence point. This means, mathematically, the Ka of your indicator should be about equal to 1 times 10 to the negative of the pH at the equivalence point. And you can predict that by knowing if you have a strong or weak acid-base titration. More about that to come. Remember that indicators are generally weak acids, but they're a fun kind of weak acid, where the acid, HA, and its conjugate base, A-, are different colors. So if the pH is less than the pKa of your acid, you're going to have mostly HA in solution, and it'll be one color. But if the pH becomes greater than the pKa of your acid, you have mostly your conjugate base, and then it's a different color. Okay, quick reminder, if you're doing a titration, you're probably using a burette, and you need to know how to read it. And burettes are read from the top down. Just to make sure you remember, take a moment. I want you to measure what volume of solution was found in the graduated cylinder here, and what volume of solution was found in the graduate cylinder at the end of the titration. And when you're done with that, go ahead and unpause the video and check your answers. Remember that you're reading to the bottom of the meniscus, and you're going from 5 down. That went a little too far. But the idea here is I would claim that this initial reading is about 5.65 because the markings are at the 10th place. So you can estimate to one more place value. You know it had to be between the 5.6 and 5.7, so, halfway, 5.65. The end of the titration was a little easier because it was exactly on the line, but you still have to estimate one more place value past the markings. So this was 37.30. And so if you want to know how much of your titrant you actually use from the beginning to the end, you just subtract. Easy peasy. There are some common lab errors that occur in titration. The most common being, of course, over-titrating and under-titrating. You added too much titrant or you added too little titrant. The thing to remember is that mathematically, you're going to use how much titrant you added to calculate how much of your analyte you have. So if you add too much titrant, it makes you look like you have too much analyte. If you have too little titrant, it makes it look like you have too little analyte. Of course, there are many other ways to mess up your titration. Those are just the two most common. If when you're filling your burette, the burette was still wet with water, well, you actually ended up diluting the concentration of your titrant. So you had to add a greater volume than you should have. And it makes it look like you added more titrant than you actually did. So in this case, you actually would calculate moles of analyte that are too large. Of course, if you accidentally add some water to your analyte in the flask, as long as you've already measured out ahead of time, it doesn't matter if there's extra water because the moles of analyte don't change. Okay, let's go ahead and talk about the different titration types for acids and bases that you need to know and recognize. First, let's talk about strong titrations, either a strong acid titrated with a strong base, or a strong base titrated with a strong acid. The language, by the way, when it says titrated with, that's the stuff you add. So a strong acid titration curve is going to start low, but when you're titrated with a strong base, you're adding more and more base, so it's getting more and more basic over time. Whereas if you start with a strong base and titrate with a strong acid, it starts basic and then it gets acidic. Now, the glory here is that because if you have a strong acid and a strong base, at the point in time where they have completely neutralized, the equivalence point, the pH is always going to be 7. And your net ionic is always going to be just proton plus hydroxide to form water. If you want to find the volume of whatever you're adding needed to reach the equivalence point, you want to use that amazing shortcut equation, MAVA equals MBVB. So, one of the quickest ways to know at a glance if you're doing a strong-strong titration is you check and find the equivalence point. Remember, the equivalence point is at the inflection in the curve. So if it's at 7, there's really strong odds that it's a strong titration. Okay, let's talk about weak strong titrations. Just like strong, weak strong can go both ways. You can start with a weak acid and titrate with a strong base, in which case you start at a low pH and you end high. And of course, if you have a weak base, well, you're starting at a high pH, basic, and then you add an acid and get more and more acidic. But did you notice where I circled on both of those? It looks a little bit different than the strong. Let's peek back at strong. The beginning of a strong titration curve is usually pretty flat, and then it just starts to go up and eventually gets really, really steep. However, a weak acid or weak base titration, it's got this little dip. So it goes up pretty quickly and then it flattens and then it goes up quickly again. And the same thing for the base. It's got that little dip at the beginning. So that's something to watch for. Also, of course, there's the pH at the equivalence point. It's not going to be 7 anymore. Remember the equivalence point, the acid and base have completely neutralized? Well, if an acid and a base completely neutralize, all that's left is a salt and water. So you're going to predict the pH just like we predict the pH of a salt. If your parent acid is weak and your parent base is strong, well, your pH is going to be basic. Strong wins. So the pH is greater than 7. Of course, weak base plus strong acid, the salt is acidic. pH is less than 7. So if you look at the equivalence point and you figure out where it is relative to a pH of 7, well, if the equivalence point is higher than 7, you probably had a weak acid and a strong base. But if the pH at equivalence point is less than 7, it's probably the other way around. When you have a weak strong titration, there's not just the equivalence point anymore. There's a new point on the graph that is very important and you need to know. It's called the half equivalence point. It's when you are halfway to the equivalence point. Sometimes it's just called the midpoint. So to find the half equivalence point, you basically find the equivalence point. So you're like, okay, this took 20 mils, I don't know, whatever it is, and you divide it in half. And that point on the curve, that is the half equivalence point. You might be thinking, wait a second, but there's a line and an arrow and it's pointing to it and it says buffer. Eek! Well, yeah. If you are halfway to the equivalence point, exactly half of your either weak acid or weak base has been titrated and converted to its conjugate. So now you have a solution where you've got equal amounts of a weak acid and its conjugate. That's an ideal buffer, a 1-to-1 buffer. Now, that means we know from our buffer math, if we have an ideal buffer, 1-to-1 ratio, well, the concentration of protons are going to be equal to the Ka of the acid. So the pH at your half equivalence point is equal to the pKa of your acid. This is fabulous, and it is one of the most common weak acid strong base questions, because you just glance at the graph. They're like, okay, great, what's the Ka of your acid? Well, you just glance at the graph, find the half equivalence point, find the pH, and you've answered your question. So these are very quick to answer. Now, you might have noticed it gets a little sneakier when it's not a weak acid and a strong base. It's actually a weak base and a strong acid. At the half equivalence point, you still have an equal amount of both, but this time it's an equal amount of base and its conjugate acid. So your hydroxide concentration is going to be equal to your Kb of the base. So the thing is, the pH still equals pKa, but you don't usually want a pKa because you care about the base, so you have to solve for the pKb. So just like always, bases have one extra step that you have to deal with. So the good news is we can still use our shortcut equation to find the volume we need to reach an equivalence point. So MAVA equals MBVB will still work, regardless of if you have a strong or a strong weak titration. Let's take a look and see how increasing the Ka value will affect the titration curve. We already know that a strong acid, when you're titrating with a base, starts off flat. Well, as your acid becomes weaker and weaker, you start to get more and more and more of that weird dip at the front. So the weaker the acid, the more of that strange dip you get, the less it looks like a strong acid, which makes sense. Please note that the equivalence point volume isn't going to change. It doesn't matter if you're titrating with a strong acid or a weak acid. That's why we can always use that MAVA equation. However, the pH at the equivalence point, that totally changes. There's one more thing I want to point out. There's a term that people use. Remember how the half equivalence point is like a perfect buffer? Now that's not true, of course, if you have a strong acid, because a strong acid conjugate is not a buffer. But for all the rest of these at the half equivalence point, you would find an ideal buffer solution. Well, notice how the titration curve stays pretty flat on both sides of the half equivalence point. That region where it stays pretty flat is called the buffering region, because you're adding a base, but the pH isn't changing much. Okay, as I mentioned, one of the most common questions if you're given a titration data is to determine the pKa or pKb of a weak acid or a base from that graph. So, in short, what you need to do is first find the location, calculate the location of the half equivalence point by dividing the volume at the equivalence point in half. And then use your data to figure out what the pH is at the half equivalence point. Is it a weak acid? You're done. pH is the pKa. That, of course, means the Ka of the weak acid is 1 times 10 to the negative of whatever the heck that pH is. If it's a weak base, just a little more effort, because the pH is the pKa of the conjugate acid. So the pKb will be 14 minus the pH at that point, which means Kb is 1 times 10 to the negative 14 minus the pH. All right, let's go ahead and try a couple of these practice problems. There are 4 different graphs to look at. For each graph, I want you to identify what kind of titration is this? Is it a strong acid with a strong base, a strong acid with a weak base, a weak acid with a strong base, or I guess there is no weak acid, weak base, so you're safe on that one. Basically, is it strong or weak, and in which way? And then you're going to figure out at the equivalence point, what is the pH? And then, if it's relevant, what would be the pKa or pKb of your analyte? Go ahead and try out the first one, and when you're ready to check your answer, unpause the video. Could you tell that it was a strong acid with a strong base? There was no dip at the beginning. It was flat, but it was acidic, so we had to start with an acid. And then, of course, got basic at the end. And if you look at the pH, or at the equivalence point, it's a glorious 7. Of course, if you've got a strong acid and a strong base, you can't determine pKa or pKb. There isn't a Ka or Kb value. They're strong. They're just big numbers. So I just say this is Na, not a thing you can do. Okay, if you haven't tried the second one, you should. And when you're ready to check your answers, unpause the video. Okay, this one started off basic, so it had to be a base titration with an acid added. But it had that little dip thing in the front. So that means it was a weak base being titrated with a strong acid. And if you try to find the equivalence point, the pH was something like, 5? Because it's a weak base, we're trying to determine what its pKb value is. Well, that means we need to find the half equivalence point. Well, 20 milliliters is where our equivalence point was, so 20 divided into, boom, our half equivalence point is going to be at 10 milliliters. So then we just have to kind of guesstimate what that pH was. To me, it looked like it was like a little above 9. How much above 9? I don't know. I called it 9.2. So to find the pKb, that of course is not the pKb. That's the pKa of its conjugate. So I just have to subtract from 14. So if I wanted to, I could find the Kb value by just taking 1 times 10 to the negative that. Okay, there are 2 more of these practice types to try. If you haven't tried them, whoops, that's not what I wanted. If you haven't tried them, you should try them. And when you're ready to check the answers, unpause the video. Okay, the first one was a strong, graph number 3. But you started with a strong base and you added a strong acid. The next one was a weak acid with a strong base. And so, as you'd expect, at the equivalence point, the pH was basic. I thought it was about 9. And so, we could find the Ka value of this acid from the graph. But to do that, we had to find the half equivalence point. So 20 mils was the equivalence point, 10 mils is the half equivalence point. And then we had to figure out about what pH that was. This one I was like, it's more than 4 but less than 5. I called it 4.5. If they want you to be more precise than that, they have to give you better data. So if it were free response, they would accept a range of answers. And if it were multiple choice, there would only be one answer even within that general range. And of course, if you want the Ka, it'd just be 1 times 10 to the negative of that. Okay, next we're going to talk about what if they don't give you the data, a titration curve? What if they expect you to sketch it yourself? What? Well, it's actually not that bad. You want to figure out, of course, the basic shape of the curve by looking at what's being titrated with what. If it's an acid titrated with a base, start low and end high for your pH. And a base titrated with an acid would be the opposite way around. Be careful. They won't always say what's added to what. Sometimes they'll just tell you what's unknown. Remember, the thing that you start with is your unknown. So if you have an acid titrated with a base, your acid concentration is unknown, and vice versa. If you're just doing a rough sketch, they do not expect you to be precise and calculate your exact starting or ending pH. You just need to make sure you're starting at a pH less than 7 and you're ending at a pH greater than 7. You're starting at a pH less than 7 if it's an acid titrated with a base. You're starting at a pH greater than 7 if it's a base titrated with an acid. They do usually carefully check your equivalence point volume, so that's where you need to make sure your math is on point. This needs to be where the steepest part is, the inflection point. But this is easy math to find it, right? You just use your VA/MA. Of course, make sure it's the volume of the solution being added that is the volume you are calculating. So the amount that you are titrating, your titrant, that's your x-axis. They also usually check your equivalence point pH, but you know how to do that. Strong titration, it's got to be equal 7. Strong acid, weak base, it's got to be acidic. Weak acid, strong base, it's got to be basic. And of course, for your final ending, just make sure your pH sure as heck better be greater than 7 if it's an acid titrated with a base, and less than 7 if it's a base titrated with an acid. You, of course, have to make sure your final value is either above or below the equivalence point. Okay, let's go ahead and try a couple of practice problems. This is a perfect problem to try out on your own, and when you're ready to check the answer, unpause the video. Okay, 30 mils of this molarity of hydroiodic acid completely neutralized this certain amount of aqueous rubidium hydroxide. So they didn't tell you if this was a strong or a weak or a what, but they gave you the names so you know from there. So this is totally a strong titration. Also, did you notice you did not know, and in fact they have you calculate, the molarity of the initial rubidium hydroxide solution? That means that's your unknown. That's your analyte. The hydroiodic acid must be the titrant. Well, they wanted you to calculate the molarity of the initial rubidium hydroxide solution. Well, that means use your MAVA equation. Figure out, since we know how much acid it took to neutralize it, we work backwards to figure out what the concentration of the base was. So we just plug in the numbers we know. And so then we can figure out that the molarity of the base is 0.316 molar. Okay, the second part says to sketch this. Well, remember that your analyte is a base, so that means you gotta start basic. How basic? I don't know. Pretty basic. And then you're adding a strong acid, so you're gonna end, acidically. I don't know, how acidic? Pick something. I tend to go high and low. And then at the pH, at the equivalence point, of course, has to be 7. But wait, the question is, where the heck is the equivalence point? Well, I'm looking for the volume of the titrant. The titrant is the thing whose concentration I know, and that is the hydroiodic acid. So my equivalence point must occur when I've added exactly 30 mils of my titrant, because that's how much they said it would take to exactly neutralize. So I find my point, pH of 7 and my volume of 30, and then here's the trick. That's got to be the steepest part, and then it just has to, flatten out at the top. That's kind of terrible. flatten out of the bottom. So it's not perfect, it's not beautiful, but it's something, right? It's got the approximate shape of a titration curve. It's got the steepest point at the equivalence point, and it starts basic and ends acidic. That's all we're looking for in a sketch. Doesn't have to be perfect. Okay, there's another practice problem. I'm not going to do all of this with you, but I do want to tell you one thing. You need one piece of information to solve this that is accidentally not in the problem. And this one's a little different. You've got a solid, you've got this many grams of this unknown monoprotic acid. I just call it HA when I don't know what it is. But the thing we were supposed to tell you and we didn't is that this is a weak monoprotic acid. And they're saying, that's great, let's go ahead and calculate the molar mass of this acid. Wait, what? This is a thing we can do. Because they told you it took this many mils of this concentration of sodium hydroxide, my yummy base. That's how much I needed to titrate it to the end point. Remember, we're hoping the end point is the equivalence point. That's when it's neutralized. So if you want to find the moles of your unknown acid, you just calculate the moles of your known base that was used to titrate it. Of course, the only point in time they're equal is at the equivalence point. Well, it's easy to find the moles of base because I know the molarity and I know the volume. Please notice I had to use liters in this calculation because I'm trying to solve for moles, and it's a pretty tiny number. So now, if you want to calculate the molar mass of this acid, well, you know how many moles you have, and you know how many grams you have. Well, molar mass is literally grams divided by moles. So I'm just dividing by the number of grams that they measured out by the moles that I calculated. So this acid had a molar mass of 101.9 grams per mole. Okay, I'll let you sketch the titration curve, but the math on that one was just a little bit different, so I wanted to make sure we went over it. And that's it. It's a lot, I know, but titrations are important. So I thank you for playing with all of the glories of chemistry.